Hey there. So we're going to continue with chapter 12, talking about nuclear shape and binding energy today. So first of all, some of the first experiments that helped determine the size of the nucleus was Rutherford's gold foil series of experiments. So what he did, of course, was he shot helium nuclei, which were he called alpha particles. They didn't at first know that the nucleus of helium was the alpha particle. So they shot helium nuclei at the gold foil, and they used the Coulomb's law to estimate how close the alpha particle got to the nucleus before rebounding. And they used that as an upper limit on the size of the nucleus itself. They used conservation of energy to do that. So what they did was they set the kinetic energy of the alpha particle, which they knew because they had accelerated the alpha particle through a potential difference or a voltage, delta V. And then if you know the voltage that you've accelerated it through, then you can set the potential energy from the change in the voltage, which would be Q delta V. You set that equal to the kinetic energy that it has, 1/2 mv squared, after it leaves the voltage. So you know the kinetic energy of your alpha particle. And then you set that initial kinetic energy equal to the potential energy of the alpha particle at the turnaround point. So remember, when a particle turns around, its speed is for an instant 0, and so that means the kinetic energy is that at that point is 0. So using conservation of energy, you set the initial energy, the kinetic energy, equal to the potential energy due to the Coulomb potential when it's at that closest point of approach. And doing that, you can solve for this equation here, where D is the distance of closest approach, K is your Coulomb constant, Z is the charge on the nucleus that you're accelerating it to. In his case, it was gold. E squared is the charge on the electron squared, and then mv squared would be twice the kinetic energy of the alpha particle. And he determined from gold that the upper limit on the size of the nucleus was 3.2 times 10 to the minus 14 meters for those first experiments. So Rutherford concluded that the positive charge of the atom was concentrated in the sphere, whose radius was no larger than about 10 to the minus 14 meters, and he called this sphere the nucleus. Okay? So now we have a unit which describes the size of a nucleus. We call it the Fermi, but if you stick with the convention of the kilo, micro, nano convention, then it's a femtometer. So 1 femtometer is 10 to the minus 15 meters, and it's also called a Fermi after Enrico Fermi, who did a lot of work in nuclear physics. So since the time of Rutherford, there have been a lot of experiments that have concluded that most nuclei are approximately spherical, that they have an average radius that's given by the radius is equal to r naught a to the 1/3, where r naught is 1.2 femtometers, or 1.2 Fermis, and a is the mass number of the nucleus. We've determined that the volume of the nucleus is directly proportional to the total number of nucleons through this, which means that all nuclei have about the same density, okay? And then as they combine, they form a nucleus as though they were tightly packed spheres, as you can see here in this picture. If you do a further study of this to figure out what the density description is, Hofstadter and colleagues at Stanford in the 1950s probed nuclear density very, very carefully, and they found that the nuclear charge density was described by this equation, rho, which is the density, is equal to some average density rho naught divided by 1 plus e to the little r minus big R divided by a, where big R is that average radius we saw in the earlier equation. T is the thickness, with about 4.4 A, where the thickness is dropped to 50% of the center value. So what this looks like is kind of a rounded off step function. So for a nucleus, of course, due to the Coulomb potential, F is equal to K, Q1, Q2 over R squared is the force, there's very, very large repulsive electrostatic forces between those protons. They're super close together, on the order of a femtometer in distance from one another. And the Coulomb force is a very, very strong force, okay? So these forces, because of their close proximities and large charges located super close together, those forces should cause that nucleus to just fly apart. So what that means is that there has to be another force that counteracts the Coulomb force that's stronger than the Coulomb force. This is known as the nuclear force, and the parent force to the nuclear force is sort of the strong force, which you might have heard about. The nuclear force is an attractive force that acts between all nuclear particles, and this attractive force is much stronger than the Coulomb repulsive force. Now you might say, well, if this is the case, right, if we have a force that's stronger than the Coulomb force, and I know that the Coulomb force is pretty strong, why doesn't all matter in the universe just come together in some big clump? And the reason for that is that the strong force or the nuclear force is extremely short range. It starts to decay off just after a few femtometers in distance, and so it's just not long range enough to cause everything in the universe to clump together into a big ball. So it's an attractive force that acts between all nuclear particles. It's very short range. It falls to zero when the separation between particles exceeds just a few Fermis. It's independent of charge, so the nuclear force is between protons and protons, protons and neutrons, and neutrons and neutrons, and it affects all of them all the same, but it doesn't affect electrons. Otherwise, the electrons would be pulled right in to the nucleus, which doesn't happen. Now you'll see here, this plot is a plot of nuclear stability. And so what you're seeing here is on the x-axis, you see the atomic number Z, that would be the number of protons, and then that's plotted versus the total number of neutrons. Now this dashed line here is the n equal to Z line. And you can see that stable nuclei happen for n equal to Z for small nuclei, right? But as the number of protons gets larger and larger, you can see that it deviates from this line and you pack more and more neutrons into that nucleus, and that's for the stable nuclei, okay? So heavy nuclei are most stable when the number of neutrons exceeds the number of protons, and that happens when Z gets above about 20 or so. Okay, now no nuclei are stable when Z is greater than 83. After you pass that, you have natural radioactive elements. They just don't stick together anymore. And that's because the total energy of the bound system, it's better when you pack more neutrons in there. They feel the attractive force from the nuclear force, right? So more neutrons you pack in, the more attractive force you get. But if you pack more neutrons than protons in there, you don't have the repulsive force from the Coulomb potential. So in order to be stable, a nucleus has to have more neutrons than protons when Z gets greater than 20, because it gives it the attractive nuclear force without the repulsive Coulomb force, and it helps them stay stable. However, once you get past a certain nuclear size, you're starting to exceed the range of the strong force, or the nuclear force, so that the nucleons on this side of the nucleus aren't really feeling that nuclear force from the stuff on this side, right? And once that size has been exceeded, then it's going to decay. It's going to be radioactive. Now, if you're talking about packing things together and having them hold together, then there has to be some sort of potential energy associated with that nuclear force. And we call that energy the binding energy. And it says that the total energy of the bound system, in this case the nucleus, is going to be less than the combined energy of the separated nucleons. And that difference in energy is the binding energy of the nucleus. It can also be thought of as the amount of energy that you need to add to the nucleus to break it apart into its components. This is an equation that we actually studied in Modern 1 a little bit, so hopefully it should at least sound a little familiar. We studied this idea when we studied Einstein's famous equation, E is equal to mc squared, okay? So what happens in the binding energy is that some of the mass from the nucleons actually goes into energy via the E is equal to mc squared equation to hold the nucleus together. So if you measure the mass of a nucleus, the mass of the nucleus will be slightly less than the mass of the nucleons if they were independent from one another and not bound together in a nucleus. That equation for the binding energy is given by, you have a binding energy, generally given in MeV, mega electron volts, because that's a convenient unit for this. And that's going to equal to Z times the mass of the hydrogen atom, plus N times the mass of the neutron, and then minus the mass of the nucleus altogether, and then times 931.494. All right? Now, it's easy to measure, well, it's not easy, but it's easier to measure the mass of a neutral atom than it is to measure the mass of an ionized nucleus, especially if you have a very large nucleus that would have a lot of electrons in it. So the reason that we stick the mass of the hydrogen in there is because it accounts for the mass of the electrons too. It's true that the mass of the electrons is 1,000 times less than the mass of your protons and your neutrons, but still it can make a difference if you have a large nucleus with lots of electrons. It can make a difference. So we keep that in the accounting by using the mass of a hydrogen atom here instead of the mass of a proton. The masses in this equation are generally expressed in atomic mass units. And remember that if you do the E is equal to mc squared conversion from atomic mass units over into energy, then the conversion constant here is 931.494 MeV per atomic mass unit. Okay? So for every atomic mass unit, if you plug in, for example, 1.66 times 10 to the minus 27 kilograms, and then you multiply that times the speed of light squared, 3 times 10 to the 8th meters per second squared, then you'll get a number once you switch over to electron volts of 931.494 MeV. So we're just skipping the middleman, okay, of the c squared and just putting that conversion in directly here. All right? Hopefully that's clear. I'd like to do an example. We did some binding energy calculations last semester in Modern 1. And so what I'd like to do is kind of mix it up a little bit. This question is slightly different than your typical binding energy question. It says the binding energy of the neon isotope, 20 neon, is 160.647 MeV. So find its atomic mass. Okay, so this involves sort of a rearranging of that binding energy equation. So what I've done is I've pulled the mass of the nucleus itself over to the left-hand side and moved the binding energy over to the right. So if you go back and you look at this equation again here, I've solved for this mass right here, MaZx, right? So to do that, first I divide both sides by 931.494, and then I add this mass of the nucleus, the bound system, to both sides and subtract that E binding over 931.494 from both sides. So that's the simple algebra that I did to get to this step right here. Now I plugged in for the number of protons and the number of neutrons. There's 10 protons in neon, and so you have 10 times the mass of hydrogen, and then there's 10 neutrons and 20 neon, so that's 10 times the mass of a neutron, okay? And then I plugged in for the binding energy that was given in the next step, 160.647 MeV, and I plugged in for the mass of a hydrogen and the mass of a neutron here in this equation, and I solved. And when you do that, you get 19.992 atomic mass units. So that should be the mass of 20 neon. Now, if you take the binding energy and divide that by the total number of nucleons in your nucleus, and then plot that versus the mass number, okay? So you're plotting the binding energy per particle versus the mass number, which is the number of particles in the nucleus, then you get this plot here. Okay, now there's a number of features about this plot. We talked about it last semester in Modern 1, but I'd like to reiterate these things now. There's a number of features about this plot that are interesting. First of all, there's a steep slope on this side that comes to a peak, and then there's a more gradual decline in the values as you go to larger nuclei. So this region right here, which is at the peak of the curve, is the region of greatest binding energy per nucleon. What that means is that those are the most stable nuclei. In other words, it's quite difficult when you're right here to pack more nucleons on, and it's quite difficult to take nucleons off. Those are the most stable nuclei. So you'll notice that a lot of natural radioactive decay chains are going to end in this region here. Okay, so that's going to happen. Now, another thing is that on the left-hand side of the peak, where the steep curve is, that's where nuclear fusion gives you a gain in energy. So, you know, hydrogen fused together to form helium in the core of stars. That's a big increase in energy right there, which is why they do it, and so on and so forth. But stars die, basically, when they get to this region of the curve, and then fusion doesn't gain them any energy anymore, and so they stop there, and that's the end of the star's life cycle. Okay? Now, on the converse, when we have nuclear power plants here on Earth and we're using fission, which is the splitting of the nucleus into smaller components, it has to be something on this side of the curve, okay, so that it's walking up towards a region of greatest binding energy, and that gains you some energy, okay? You'll notice that the slopes on the left-hand side here for the fusion side give you greater gains in energy as you fuse because the slope is steeper than the slopes on this side. You'll get less gains in energy through fission because the curve isn't as steep on that side. Okay, that's all stuff that I just said while looking at the curve. Now, the binding energy is about 8 MeV per nucleon for nuclei with an atomic mass unit greater than 50. If you look back at that curve, you'll see that, you know, it does have a sort of steady decline, but the decline isn't very steep, and so 8 is about average and normal. What this suggests is that the nuclear force is saturating, and that a particular nucleon can interact with only a limited number of other nucleons, and that's just simply because of the range of the nuclear force. All right. Okay, I'd like to work one more example for you, and this has to do with the energy that it takes to remove one nucleon from your nucleus, okay? So this one is, find the energy needed to remove a neutron from the nucleus of the calcium isotope 42 calcium. And then find the energy needed to remove a proton from this nucleus. And then why are these energies different? Okay, so let's go through how to handle this because it's a little different, not much different, but a little different than some of the binding energy calculations. So removing a neutron from 42 calcium is going to leave 41 calcium. It's still calcium because you haven't removed a proton, but you've got a different isotope of calcium. Now, there's tables of atomic masses. There's one in the appendix of your textbook, okay? You can also find this information online. From the tables of atomic masses, you can find that the mass of 41 calcium, okay, and you can also look up the mass of 42 calcium. Taking the mass of 41 calcium and then adding in the mass of a free neutron, which is given here, 1.008665 atomic mass units. If you add those two masses together, you get 41.970943 atomic mass units. Now you might be thinking, can't I just round that? No, I'm sorry. When you're doing binding energy calculations, the difference in the masses is sometimes so small that you really do need all those digits, okay? So however many digits it gives you in the atomic mass table at the end of your textbook in the appendix, that's how many digits you should use and keep when you do these kinds of calculations. Otherwise, you're going to get significant rounding errors, and when you do your homework, WebAssign's going to tell you your answer's wrong, even though your approach and your strategy is right. Okay, so keep all those digits until the end. Now, if you look at the mass of the 41 calcium plus the neutron, you get that mass. Now, let's find the difference between the mass that we just found, 41.970943, and the mass of 42 calcium, which you can also look up at the table. When you do that, you'll see that the mass of the 41 calcium and the free neutron is larger, of course, than the mass of the 42 calcium. So if you take that energy difference, or mass difference, energy difference, same difference, delta M, then you get 0.012321 atomic mass units. So the binding energy then for that missing neutron is that delta M times C squared, or times the conversion from MeV to atomic mass units, 931.494, and you get 11.48 MeV. Okay? So that's how much energy it would take to remove just one neutron, all right? Now, if you remove a proton, then what you've got is not calcium anymore. It's actually potassium, which has a value of Z that's 1 less than the value of calcium, okay? So you can look up the mass of the potassium isotope 41 potassium, because you'd still have all those neutrons, right? You've only lost one nucleon. And then we're going to follow a procedure that's really similar to what we did in the previous example. Okay, we're going to take the mass of 41 calcium and add it to the mass of a free proton, and we get 41.96965 atomic mass units. Now we take that number and we take the difference between that number, which is going to be larger than the mass of 42 calcium, the bound system, and we get 0.011028 atomic mass units. Then we multiply that times the conversion from MeV to atomic mass units, and we get 10.27 MeV. Okay, so you can see that this energy to remove one neutron is actually greater than the energy to remove one proton. So why the difference? Well, the neutron had only attractive forces acting on it, whereas the proton also had the repulsive Coulomb forces, and that would decrease the binding energy for the proton relative to the neutron. So that can be seen in this simple calculation. Okay, well, that's it for today. I hope you understood, but if not, shoot me a question, and see you next time.